Okay, so we'll start the discussion session 6. So we have completed the fuzzy arithmetic part, right? And the next module is about fuzzy relations, which are fuzzy extensions of the classical relations that we all have studied uh, so far. So just to recall, if I have if I have two universe X and Y, so by a universe I mean nothing but a crisp set, then a crisp relation R from X is a crisp subset of X cross Y, right? So it's basically a subset of X cross Y. Or in other words, it's a member of the power set of X cross Y, right? So such a relation, by the way, is called as a binary relation because we are talking about two universes, namely X and Y. So more broadly, we can define a relation over more than two universes. So uh, particularly, you give me a positive integer n greater than equal to 2 and n number of universes, so x1, x2, all the way to xn, then a crisp relation R on these xi's is nothing but a crisp subset of x1 cross x2 cross xn. So the Cartesian product of the sets xi's. Or in other words, R is a member of the power set of the Cartesian product of the set xi's. Now, we can study relations on three sets or four sets or more generally n sets, but it turns out that binary relations are the most interesting ones. So we all are familiar with functions, right? So functions are an example of binary relations. So binary relations are the most interesting ones, and therefore we'll focus on them. So given universe X and Y, we just saw that a crisp binary relation R from X to Y is a crisp subset of X cross Y, right? Or in other words, R is a member of the power set of X cross Y. Now, these crisp relations are suitable for modeling crisp relations. What do I mean by that? So I should write crisp relationships. So crisp relations are suitable for modeling crisp relationships. And what do I mean by a crisp relationship? It's a relationship that is either exactly true or exactly false, right? So if you consider a statement like Modi is the Prime Minister of India, we know that it is to be true. We know that it is exactly true. It does not make sense to say that Modi is the Prime Minister of India to extend point 0.5, right? So this relationship of being Prime Minister of is a crisp relation. It's a crisp relationship, and therefore we can model it using a crisp relation. So more specifically, we can define X to be the set of all people on Earth and Y to be set of all countries, then this relation Pm of it's a crisp subset of X cross Y. More specifically, we say that X comma Y belongs to this relation Pm of if and only if X is the prime minister of country Y. Right. So similarly, we have a couple of other examples of crisp relationship. Father of is again an example of a crisp relationship. Is located in is example of another crisp relation. So crisp relationships that are exactly true or exactly false, can be modeled using crisp relations. But many interesting relationships that exist in the world are not exactly true or not exactly false, right? So, for example, if you consider a statement like Mumbai is warmer than Delhi, then this whole relationship of warmer then is a matter of degree. It does not make a lot of sense to say uh, that Mumbai is always warmer than Delhi, right? So it makes much more sense to model this relationship warmer than as a relationship that is graded. So it's a graded relationship. Similarly, very tall then is an example of another relationship that is more meaningfully captured using a graded relation as opposed to a crisp relation that would dictate that either it is the case that Dutch are very tall than Indians or it is not the case that Dutch are very tall than Indians, right? So all this goes out to suggest that there is a natural motivation to define a fuzzy counterpart of classical relations or crisp relations, right? So more specifically, if you give me universe X and Y, then a fuzzy binary relation R from X to Y is a fuzzy subset of X cross Y. Okay. So in other words, R is a member of the fuzzy power set of X cross Y. So fuzzy relations are more suitable to model graded relationships, relationships like warmer than or very tall than. So let us take a more concrete example. Uh, Suppose X is the set of all countries and Y is the set of all currencies. Then we can define a relation R on from X cross Y as follows. We'll say that X comma Y belongs to R if and only if Y is official currency of X, right? So an example could be India and Indian rupees or US and US dollars, right? So this is an example of a crisp binary relation from X to Y and is official currency of it's a relationship that is either going to be exactly true or exactly false. Therefore, it makes sense to model such a relationship using a crisp binary relation. Let us take another example. And in this case, our universe X is set of two cities, New York City and Paris, and Y is a set of three cities, Beijing, New York City, and London, right? And let us consider this relationship is very far. Now, is very far does not seem to be a crisp relationship, right? It, it makes sense that to model it using a fuzzy relation, right? Because it is much more meaningful to say that Paris and Beijing are way far apart in comparison to Paris and London, right? Because Paris and London both happen to be in Europe. So is very far is much more meaningfully captured using a fuzzy relation, right? And we can define such a fuzzy relation like this. So R is a fuzzy set over X cross Y, right? And we specify that fuzzy set like this. So the degree of relationship between New York City and Beijing is one, which means that R, which means New York City and Beijing are really far apart, right? And membership of New York City, comma New York City in R is zero, which means that it is absolutely false that New York City is very far from New York City, which makes sense, right? Because the distance between a city and itself is zero. So it does not make sense to say that New York City is really far from itself. Similarly, the membership of New York City, comma London in R is zero point 0.6, and that should be interpreted as that it is it is like fairly true that New York City and London are far apart. And similarly, you have membership of Paris, comma Beijing, Paris, comma New York City, and Paris, comma London. So the point is that graded relationships, relationships that are not exactly true or exactly false, are more suitable to be captured or modeled using fuzzy relations, right? And for a fuzzy binary relation from X to Y is nothing but a fuzzy subset of X cross Y. Okay. Now, so this is the fuzzy relation that we just saw. Now it turns out that we can represent R much more compactly using a matrix, or more specifically, a membership matrix. So the members of X are listed here. So the universe X are listed row wise, and members of universe Y are listed column wise. And then the membership of X comma Y in this relation R are listed as entries in this matrix. So the fact that we have one corresponding to column Beijing and row New York means that membership of New York and Beijing in relation R is 1. We have a point 3 here corresponding to row Paris and column London. That means that the membership of Paris, comma London in relation R is point 0.3. So you get the point, right? It's nothing complicated. So when our underlying universe X and Y are finite, then R can be compactly represented using a membership matrix. Okay. So more generally, if you have a finite universe X consisting of n elements and a finite universe Y consisting of m elements, then a fuzzy binary relation from X cross Y can be represented by a matrix like this. So this is a n by m matrix, and its entries essentially come from 0, comma 1. So it's a member of 0, comma 1 raised to n cross n, right? So the rows corresponds to the elements x1, x2, all the way to xn. So the rows are elements of the universe X, and columns corresponds to the members of universe Y, right? And at the I comma jth entry of this membership matrix is the degree, or is the membership of xi comma yj in the relation R, right? So we are going to use this notation to indicate the membership matrix of R. Okay. So R is a fuzzy relation from X cross Y, and square brackets R is essentially its membership matrix. And why we are doing this would become clear in the coming slides. But the idea is basically this, that if you have finite universe X and finite universe Y, then a fuzzy relation from from X to Y can be compactly represented using a n by m matrix. And the entries of this matrix are essentially numbers in the unit interval, right? Now, before I go further, I want to discuss a concept called quantification. And the reason I want to do that is because once we know what quantification is, a lot of definitions related to fuzzy relations would become very intuitive. Okay, so so quantification is not something unique, is not something new. We have all been doing quantification. It's just that we never really paid attention to it. So in classical logic and set theory, we often quantify predicates. So what do I mean by predicate? Just think of predicate as a property, right? So in general, a property phi x. So phi is called as a predicate, and it involves one variable x. And this basically states some property of x, right? So phi of x can be x is a real number. Or another example of a predicate could be x is a matrix of size 2 cross 3, right? So generally speaking, a predicate of x involving variable x states some property about x, right? We can define it rigorously, but I don't want to do that. Just think of a predicate as a declarative statement. which tells you something about the variable x. Okay. So for example, we have often seen statements like this in math, that for every x in R being the set of all real numbers, x squared is greater than equal to 0. So this is an example of a quantified statement. So here phi of x is basically x squared greater than equal to 0. And this statement is essentially of the form, for every x in R, phi of x holds, right? So we have a predicate phi of x and we are quantifying it over all real numbers. So when we say that for every x in R, we are essentially doing a quantification. We are asserting that x comes from real numbers. So we are quantifying where x come from, right? So this is an example of something called as universal quantification. So whenever we have a for all, it's an example of universal quantification because we are asserting that for all values of x that come from the set R, this predicate phi of x, which is x squared greater than equal to 0, holds, right? Now we can do another kind of quantification, which is called as existential quantification, which is denoted by this symbol, there exist. So for example, we can write something like there exists a real number x such that x square equals to 2. So in this case, our predicate is x square equals to 2, and we are saying that there exists x in R such that phi of x holds, right? So what we are doing here, we are quantifying that there exists some x, right? As opposed to the first statement in which we are saying that for all x in R, or in other words, x is universally quantified. It can come from any part of R. On the other hand, the second statement says that for some x in R, so there exists some element in this big set of real numbers for which the predicate phi of x holds, right? So quantification means that we have a predicate and then we are specifying some values, some range of values for the variable in that predicate, right? So if we have a predicate phi of x, we are universally quantifying it would mean that we are dealing with a statement like this. For every x in R, phi of x, when we existentially quantify it, that means there exists R such that phi of x. In this case, phi of x is x squared equals to 2. And we can have a combination of existential quantification and universal quantification. So for example, consider statement 3. So for every x in R, there exists n in Z such that x is less than n, right? So here we are doing a universal quantification and then we are doing an existential quantification. And here our predicate actually involves two. So maybe I'll write this here. So here our predicate involves two variables, x and n. And this predicate essentially says that x is less than n. So this is an example of statement we are doing where we are doing a combination of universal and existential quantification. Okay. So nothing extremely new. We have been doing it for like since high school math. Now, if you give me a predicate phi of x, then as I just said, we can existentially or universally quantify the variable x over some set capital X, right? And this set capital X is often referred to as the domain of quantification. So in the first example, the domain of quantification was real numbers. In the second example, again, the domain of quantification was real numbers. In the third statement, we have two quantifiers and sorry, we had two quantifiers and the domain of first quantifier was R and the domain of second quantifier was Z. Okay. So to summarize, given a predicate phi of x, we can existentially or universally quantify the variable x over some set x called the domain of quantification. And this is existential quantification and this is universal quantification. So EQ and UQ. Now, let us examine when does this statement, this existentially quantified statement, there exists x in set x such that phi of x is 1. What is the truth value of this statement? Now, this statement becomes true. Sorry. So, is true if we can find an x naught in x such that phi of x naught is true, right? This statement, this existentially quantified statement that there exists x in set x such that phi of x is true if we can find a x naught, some element in our set capital X, such that predicate phi of x naught is true. Or in other words, you take the truth value of phi of x. So t of phi of x means truth value of phi of x. And then you take its maximum over all members in your set capital X. If this maximum turns out to be 1, then this would mean that there exists some x naught in your set capital X as the truth of phi of x naught was 1. Because if for all x, the truth of phi of x were to be 0, then this maximum would have been 0. But since it is 1, then that means that we are able to find an x naught in our set capital X, the domain of quantification, such that the truth of the predicate phi of x naught is 1. Right? And similarly, when this maximum of t of phi of x is 0, then that would mean that for all x in the set capital X, this predicate phi of x is false. This was same as saying that there exists x naught such that phi of x holds is false. So in other words, the truth value of this existentially quantified statement can be expressed in this manner. You simply take the maximum of truth of the predicate phi of x as x varies your entire domain of quantification. In a similar manner, the truth value of this universally quantified statement for every x in set x such that phi of x is given by taking the minimum of truth value of phi of x as x varies over the entire domain. Okay. So I hope this makes sense to you. And in case, so this is basically what I wanted to like establish. Now let us take a specific type of predicate. A predicate that says that an element is a member of some set A. So I have a universe X, okay, and I take a crisp subset of X. And then I am interested in this predicate that X belongs to A. Now this predicate can be existentially quantified or it can be universally quantified. So this statement tells you that all members of X is a member of A. Sorry, there exists an element, sorry, this means that there exists an element X in your set capital X so that X belongs to A. And this universally quantified statement tells you that for all member X in set capital X, X is a member of A. Okay. Now, how do I compute the truth value of this existentially quantified statement? So that is the maximum of truth value of X belongs to A when X varies over X. Right? This is what we just saw. And what is the truth value of this predicate X belongs to A? When we will say that X belongs to A is a true statement. Precisely when the characteristic function of A evaluated at X equals to 1, right? When do we say that the characteristic function of some set at an element is 1? When that element belongs to that set. Okay. Similarly, when we will say that the truth value of x belongs to a is 0, when the characteristic function of a at x is 0, right? So in other words, the truth value of this statement, this existentially quantified statement, is essentially maximum of the characteristic function a of x, where x varies over your universe, or which in this case also is the domain of quantification. Similarly, the truth value of this universally quantified statement for every x in set capital X, such that phi of x, and here phi of x is basically x belongs to it, is given by this, as we just saw. And the truth value of x belongs to a is nothing but the characteristic function a, characteristic function of a. So this minimum is nothing but the minimum of characteristic function of a over x, where you are taking the minimum over your entire universe, right? Now, what if instead of a crisp subset a of x, I had a fuzzy subset a of x? Then how do we make sense of a statement like there exists an element x in set capital X such that x belongs to a? How do I compute a truth value of a statement like this? Now we do that by fuzzifying these classical definitions. So I hope it is clear to you by now that a lot of things in fuzzy set theory are defined by looking at their classical counterparts and then replacing the classical definitions by the fuzzy definitions, right? So in fuzzy equations, we took inspiration from classical equations. So we have equations a plus x equals to b. And then how did we define fuzzy equations? We replaced a by b by fuzzy numbers a and b, right? So the point is that a lot of definitions in FST and FL come from fuzzifying the classical definitions. So, and that is precisely what we are doing here. So given a universe X and a fuzzy set A over X, the truth value of this existentially quantified statement, there exists X in A such that X belongs to A, is given by taking maximum of the membership function of A over the entire universe X. So here we had characteristic function. And what does characteristic function translate to in the fuzzy context? Membership function, right? So you essentially replace the characteristic function by membership function, and that would give you the truth value of this existentially quantified statement. Similarly, the truth value of this statement, this universally quantified statement for every x in set capital X, x is an element of fuzzy set A, is given by taking the minimum of the membership function of A over the entire universe X. And in case X is infinite, then we replace max by supremum and minimum by infimum, right? Because when x is infinite, then the notion of maximum and minimum may not be meaningful all the times. So therefore, we take the supremum and infimum instead, right? So to summarize, we often quantify predicates in mathematics that we have done so far, right? It is not something unknown to us. So we do two types of quantification, namely existential quantification, when we're asserting that some element exists for which a property or a predicate phi holds. When we universally quantify a predicate, we are asserting that for all elements in some domain, a predicate phi holds. Now I can take a particular kind of predicate, namely x belongs to A. Then we can compute their truth values like this. Now a natural question is, what if we have the predicate x belongs to A, but A is a fuzzy set? Then how do I make sense of a statement like this? X belongs to A such that X is a member of A, and for every X in X, X is a member of A. And we do it by this, right? And the inspiration for giving these definitions come from, again, looking at how things behave in the crisp setting. Okay, so the reason why I did all this is because now the definitions of domain and range and even the definition of composition of relations would make a lot of sense to you. So suppose I have a crisp binary relation R from from X to Y, that is R is a crisp subset of X cross Y, or in other words, R is a member of the power set of X cross Y. Then the domain of R and range of R are defined in this manner. The domain of R is the set of all elements in the set capital X for which there exists an element in set capital Y such that X comma Y belongs to R, right? And this, by the way, is a crisp subset of X. So I hope you can see that. And the range of R is the set of all elements Y in set capital Y for which there exists an element in set capital X such that X comma Y belongs to R, right? So this is the like intuitive definitions, right? So in other words, domain of R is a crisp subset of X and range of R is a crisp subset of Y defined in this manner. That X belongs to domain of R if and only if there exists a Y such that X comma Y belongs to R. And range of R is a crisp subset of Y such that defined by Y belongs to range of Y if and only if there exists an X in the set capital X such that X comma Y belongs to R. So these are the definition of domain and range of crisp relations. Now looking at these definitions, we propose the definition of domain and range of fuzzy relations. So given a binary fuzzy relation R from X cross Y, that is R is a fuzzy subset of X cross Y, the domain of R is defined to be a fuzzy subset of X. So in the classical setting, domain of R was a crisp subset of X. So naturally in the fuzzy setting, the domain of R is a fuzzy subset of X defined as this. So there exist would become supremum, as we just saw, and this quantification was being done over Y. So this would become supremum over all Y. And X comma Y belonging to R would become the membership of X comma Y in R. So in other words, the membership of X in domain of R, which is a fuzzy subset over X, is nothing but supremum of mu R X comma Y, that is the membership function of R, over the set capital Y. In other words, the domain is given in this manner. Similarly, in classical setting, range of R is a crisp subset of Y. So in the fuzzy setting, range of R would be a fuzzy subset of Y. And how is this range defined in the crisp setting? We say that there exists X in the set capital X such that X comma Y belongs to R. So when we translate this into fuzzy terms, there exists would again become supremum. And here we are taking quantification over X. So supremum would be X over X. And X comma Y belonging to relation R would become mu R of X comma Y. So this is how the range of R of a fuzzy relation R is defined. So the range of a fuzzy relation R from from X to Y is a fuzzy subset of Y, and it is defined in this manner. Okay, so supremum over set X. So the point is, you can simply look at these definitions and remember them, but it makes sense to actually understand why these definitions are look like this. Now, why are we taking supremum? Why not infimum or some other operation? And the motivation for this definition actually comes from looking at how domain and range are defined in the classical setting and then fuzzifying them. And fuzzifying this definition involve fuzzifying these existential quantifier. And that is why this whole sermon on existential and universal quantification is, makes sense. Anyways, so long story short, this is how domain and range of a fuzzy relation R is defined. So let us do an example. So we have a universe X consists of three elements and a universe Y that again consists of three elements. And R is a binary fuzzy relation from X cross Y that is described in this manner. This is the membership matrix. So remember, the rows corresponds to elements of X and columns corresponds to elements of Y. So this entry point 4 indicates that the membership of X2 comma Y2 in relation R is 0.4. And we need to identify which of these four options are correct. So domain of R is a normal fuzzy set, range of R is a normal fuzzy set. So first of all, R is a fuzzy set, is a fuzzy relation from X cross Y, which means domain of R would be a fuzzy set over X, and range of R would be a fuzzy set over Y. And how is this fuzzy set domain of R is defined? It is the supremum of the membership function as Y belongs in the set capital Y. Here our Y is finite. So this supremum is nothing but maximum. So if I were to compute the membership of X1 in domain R, I need to compute the maximum of mu R X1 comma Y, where Y varies over your set capital Y. Or in other words, you just need to look at the maximum of the first row of this membership matrix, right? Because this first row essentially lists out the membership of X1 comma Y, where Y is varying over the set capital Y, right? And we are interested in computing this maximum. So all we have to do is look at the first row, that is the row corresponding to the element X1 of the membership matrix, and compute the maximum element in that row, which in this case happens to be 0.8. So maximum of 0.2, 0.5, and 0.8 is nothing but 0.8, right? So in other words, when your underlying universe is finite, so X is finite and Y is finite in this case, then you can easily compute the domain and range of relation by simply looking at the membership matrix and taking the maximum row wise and column wise. So domain of R, which is a fuzzy subset over X. So the membership of X1 in domain of R is the maximum element in the first row, which is 0.8. Membership of X2 in domain of R would be the maximum element in the second row, or I should say maximum membership in the second row, which is 1. And the membership of X3 in domain of R would be the maximum membership in the third row, which is 0.6. And it is clear that this is normal because X2 belongs to domain of R with membership 1. So this is definitely correct. Similarly, range of R is a fuzzy subset over Y. And how is the membership function of Y in range of R given? It is obtained by taking the supremum of the membership function where your variable X varies over the set capital X. Since our set capital X is finite, taking supremum over it is equivalent to taking maximum over it. So therefore we get this expression. So if I were to compute the membership of Y1 in this range of R, then that would essentially mean that I'm taking the maximum value of the membership function of R at X comma Y1, where X varies over X. So X is X1, X2, and X3. Or in other words, we are essentially looking at the maximum membership value in the first column of our membership matrix R, which in this case happens to be 1, because 0.2, 1, and 0 maximum value is 1. So to conclude, range of R, which is a fuzzy subset over Y, so the membership value of Y1 is the maximum membership value in the first column. Membership value of Y2 in range of R is the maximum membership value in the second column, which is 0.5. And membership of Y3 in R would be the maximum membership value in the third column, which is 0.9. It's evident that this is a normal fuzzy set because the membership of Y in range of R is 1. The second option is also correct. The third option says that the cardinality of domain of R. So I hope everyone remembers how is cardinality of a fuzzy set defined. So if A is a fuzzy set over universe X, then the cardinality of A is essentially obtained by summing the membership function of A over all the elements of the universe. Right? So this was taught in week 1, I guess. I hope you remember all this. The third option has to do with the cardinality of domain, and the fourth option has to do with the cardinality of range. So let us compute. So, so maybe I'll compute the cardinality of domain here. This is right. And what is the sum of the membership, sum of all the membership values that the membership function of domain of R takes? It's 0.8 plus 1 plus 0.6.
Excuse me, sir.
Yes.
Sir, slide is not moving, sir. Sir,
Is it? Yeah, I can hear you.
sir, am I audible, sir?
Yes, you are. Am I
Sir,
audible?
slide is not moving, sir.
Yeah, I get your point. Jaya or Nirmala, can you confirm if I'm audible?
Yes, sir, you are audible.
And the
Sir,
slides are
I
moving
could
as well.
able to, sir, I'm able to listen you, sir. But a slide is not moving, sir.
Okay.
Oh,
Did you see a change in slide?
okay. Sorry, sir. Let me check my connection, sir. Sorry.
You're able to see the movements in slides, Nirmala, right?
Yes, sir, I'm able to see it.
Okay, so maybe there's a problem on your side. Uh, Yogas, whatever. Anyways, so the cardinality of domain of R, you simply add all the membership values that the membership function of domain of R takes. So that is 0.8 plus 1 plus 0.6. So 1.8 plus 0.6, so that is 2.4. So C option is also correct. Similarly, you can compute the cardinality of range of R. So all you have to do is sum all the membership values that the membership function of range of R takes. And that is 1 plus 0.5 plus 0.9. So this is again 1.5 plus 0.5 to 2.4. So it turns out that all the four options are correct. So I hope everyone got this, what exactly we are doing here. Is there any confusion? Is there any doubt? Can someone unmute and confirm, or should I move ahead?
Sir, it is clear, sir. Mm.
Okay. Okay, so let us now. We started with the concept of binary fuzzy relations. Then we defined their domain, and then we defined their range. Now the next natural step is, if I give you two binary relations, R and Q, how do I compose it? Now we will define how to do that, and we'll take the motivation for their definition by looking at the classical setting, right? So it's a recurring theme. In order to define something in a fuzzy context, we look at the definition in the classical context and then we fuzzify it, right? And this is how I would suggest all of you to study fuzzy set theory, because in a sense, fuzzy set theory generalizes classical set theory or classical logic, right? So it makes sense to look at the classical motivations and then study the fuzzy concepts. So, anyways, so R is a binary relation. It's a crisp binary relation from X to Y, right? So it's a member of the power set of X cross Y, which is same as saying that R is a binary crisp relation from X to Y. And we have a relation Q from Y to Z. Then the composition of R and Q, which is denoted by this symbol, is a crisp relation from X to Z that is defined in this manner. So you pick all the pairs X comma Z for which you are able to find an intermediate element Y in the set capital Y so that X and Y are related, that is X and Y belongs to R, and Y comma J, Y comma Z belongs to Q. So this is a definition that all of us are familiar with, right? So it's taught in class 11. So if I were to reformulate this definition, R composed with Q is a crisp subset of X cross Z defined by X comma Z belonging to R composed Q if and only if there exists an element Y such that X comma Y belongs to R and Y comma Z belongs to Q. Okay. And we've used this classical definition and fuzzify it to obtain the definition of composition of fuzzy relations. Okay. So before that, I'll just make a point that studying composition of binary relation makes sense, right? It's not just of theoretical interest, but it's of practical interest as well, because many crisp relationship that exist in real world can be seen as composition of two relations. So for example, the relationship of being uncle can be seen as composition of relationship of being sibling and being parent. So what do I mean by that? So we say that X is an uncle of Z. A human X is uncle of human Z. If I'm able to find a human Y such that X is a sibling of Y or X has a sibling Y and Y is a parent of Z, right? That's how the relationship of uncle is defined. I am an uncle of Z if I have a brother or sister Y and Y is a parent of Z. So in other words, the relationship of uncle can be factorized into these two relationships. So the point is that studying composition of binary relations is of practical interest as well, and therefore we should spend our energy on all this. Okay. Now we'll define the composition of fuzzy relations. So suppose X and Y and Z are universes. R is a fuzzy relation from X cross Y. So notice that I'm dropping the qualifier binary. I'm no longer going to repeatedly say that R is a binary fuzzy relation from X cross Y. Simply saying that R is a relation from X cross Y should suggest to you that I'm talking about a binary relation. Anyways, we have universe X, Y, and Z. R is a fuzzy relation from X cross Y, from X to Y, and Q is a fuzzy relation from Y to Z. Then the composition of R and Q, which will be denoted by this symbol, R circle Q, is a fuzzy relation from X to Z. Or in other words, it's a fuzzy subset of X cross Z. And how is this fuzzy set defined? How is the membership of this fuzzy set defined? It is defined in this manner. So you take minimum of mu R X comma Y and mu R Y comma mu Q Y comma Z. And then you take the supremum over all Y. Now, where does this definition come from? So in classical setting, this is how composition of two class relations R and Q are defined. We say that X comma Z belongs to R composition Q if we can find an intermediate element Y such that X comma Y are related, that is they belong to R, and Y comma Z are related, that is they belong to Q. Now, this translates to mu R X comma Y. This translates to mu Q Y comma Z. And then we have a conjunction, we have an AND. What is the fuzzy counterpart of AND? It's the minimum Tino. And then we have an existential quantification here. How do we fuzzify existential quantification? By taking supremum. Supremum over what? The domain. And domain here is Y. And this is precisely how composition of two binary relations are defined. So we just looked at the classical definition, the crisp definition, and fuzzified it. Okay. So this composition is also referred to as max-min composition or sup-min composition. Why sup-min? Because we are using minimum. Notice that we translated this and in the classical definition to minimum T-norm. We could have used any other T-norm. We could have used an arbitrary T-norm I. But since we are using the particular T norm minimum, that is why this composition is often referred to as the submin composition. Okay. So because we are taking supremum at the front, and min because we are using the minimum T norm, right? And in case y is finite, then this supremum would translate into maximum, sorry. And that is why sometimes it's also referred to as maximum composition of R and Q, right? And sometimes the symbol used is this. This subscript M indicate that we are using the minimum T norm. Okay, so I hope the definition of composition of two fuzzy relations is clear to you. This definition does not come out of blue, but it is a simple extension of the classical definitions, right? So we'll define the composition in a very general setting now. So suppose I have universe X, Y, and Z. We have fuzzy relation R from X to Y, fuzzy relation Q from Y to Z, and we have a T norm I. Then the max I composition of R in Q, or sup I composition, whatever you want to call it, denoted by this symbol, R circle Q, and you put a subscript of I on the circle, is a fuzzy relation from X to Z. That is, it is a fuzzy subset of X cross Z. And the membership of it, the membership of this relation, it looks like this. So you take the supremum of I of mu Rx comma Y comma mu Ry comma Z, and then you take the supremum over the entire Y. Okay. And in case Y is finite, then sup becomes minimum, and hence max I composition. So I hope this definition, you understand this definition now. Because generally in books, you just find the definition straight away, and it's kind of hard to motivate it unless you know that there exists, and for all these quantifiers are extended into the fuzzy setting by supremum and infimum. Anyways, so let us do an example to make the definitions that we have discussed so far concrete. We have universe X, Y, and Z. X consists of two elements, Y consists of two elements, Z consists of three elements, and we have relation R from X to Y, and relation Q from Y to Z. So this is R. This is the membership matrix of R, and this is the membership matrix of Q. So recall, rows of R, this membership matrix R, corresponds to elements of X. So these are X1 and X2. Columns corresponds to the elements of set Y, that is Y1, Y2. And similarly, Q is a relation from Y to Z. So the rows of Q, membership matrix of Q, would correspond to elements of set Y, that is Y1, Y2. And columns of membership matrix of Q would correspond to elements of Z. Okay. Now, let us compute the maximum composition of R and Q. So we know that it is going to be a fuzzy relation from X cross Z, from X to Z, or in other words, it's going to be a fuzzy subset of X cross Z. And the membership of this composition relation is given in this manner. So maybe I can use, okay, so maybe I'll first write this and then, right? But since Y is finite, so I should have written maximum here. Okay. Now, since elements of X, Y, and Z are indexed as 1, 2, 1, 2, and 1, 2, and 3, it makes much more sense to actually right? So basically, I'm just translating this definition in terms of indices because since elements of X are nicely indexed, X1, X2, I can write the membership of Xi comma Zk in this composition relation as maximum of this quantity. So let us now compute the membership of say X1 comma Y2 in this composition. So that would be maximum of this thing. Now, when we put Z equals to 1, we'll have to take minimum of and when we put Z equals to 2, we have to take the minimum of this thing. Okay. So what is x1 comma y1? The membership of x1 comma y1 in R, it is 0.4. So this is 0.4. What is the membership of y1 comma z2 in Q? It's 0.4 again. And what is the membership function or membership of x1 comma y2 in R? It's 1. And what is the membership of y2 comma z2 or y2 comma z2 in Q? So that is this. So it's 0.5. So when you take the minimum of this two number, you get 0.4. And when you take the minimum of this two number, you get 0.5. And when you take the maximum of this whole thing, it becomes 0.5. Okay. So basically, I'm just using this definition to compute the membership of x1 comma y2 in the composition of R and Q. Okay. Now, I think it's clear to you that doing this maximum and minimums is kind of tedious, right? You have to be very careful of all of what exactly you are doing, and even a minor mistake can make the entire calculation wrong. So I want to propose an alternative perspective on how you can actually look at this composition. And that I'm going to do by making an analogy with matrix multiplication. So we all know how to multiply matrices, right? And that is something that we have done a lot of times. So we are really good at it. Now let us see if this composition of relations can be seen as some kind of matrix multiplication. Okay. So I'm audible, right?
Yes, sir.
Yes,
Okay.
sir.
Okay. So suppose R is a fuzzy relation from X to Y and Q is a fuzzy relation from Y to Z, and the universe X, Y, and Z are finite. So suppose X is X1, X2 all the way to X, and Y is Y1, Y2, Ym, and Z is Z1, Z2, Zp. Then we know that this matrix R, so we can represent the relation R using a matrix, right? An n by m matrix whose entries come from unit interval. And this is how the matrix is defined. Rows corresponds to elements of X and columns corresponds to elements of Y. Similarly, the relation Q can be represented by a M by P matrix with entries in unit interval. Again, the rows correspond to elements of Y and columns corresponds to elements of Z. Now, suppose I give you a t-norm I and I am interested in computing the composition of R and Q with respect to this t-norm I. Then we know that it is a fuzzy relation from X to Z. Now, we will see how we can easily extract the matrix representation of this composition by performing a special kind of multiplication on matrix representation of R and Q. That is, we can obtain by doing some kind of operation star on the matrix representation of on R and Q. So to motivate that operation star, we first look at the matrix representation of this composition. So R has a fuzzy relation from X to Y, Q has a fuzzy relation from Y to Z, and therefore the composition of R and Q with respect to T norm I would be a fuzzy relation from X to Z. And this is how that fuzzy relation, the matrix representation of that fuzzy relation would look like, right? So X had n elements, Y had m elements, Z had p elements. So therefore, X cross Z would have n cross p elements. So this matrix is of size n by p, and entries come from unit interval. And this is how the entries of the matrix look like, right? So rows would correspond to elements of X, and columns would correspond to elements of Z. Now, I'm just using the definition. So membership of X1, Z1 in composition of R and Q is this. So you take the maximum over all J of I of mu R X1, Yj and mu Q of Yj, Z1. Right? Just using the definition here, nothing more. Similarly, the membership of X1, Zp in this composition relation R circle Q is given in this manner. To take the maximum of I of mu R X1, Yj, mu Q Yj, Zp as Z varies over 1 to P. So in other words, you just write the matrix representation of this composition relation, and then you write out the entries of this matrix using the definition that we have done so far. And just remember that it looks like this. Okay. Now let us look at the standard matrix multiplication of R and Q, of membership matrix R and membership matrix Q. If I were to multiply matrix R and matrix Q using the standard matrix multiplication, then what we would get? So the 1,1th entry of the standard matrix multiplication of R and Q would be obtained by multiplying the first row of R with the first column of Q, right? In other words, we will multiply the entries of the first row of R with the first column of Q entry wise, and then we'll add all of them. That's how matrix multiplication is defined. So in other words, in general, I, kth entry of this matrix multiplication of R and Q would be obtained by multiplying the entries of the ith row of R and kth column of Q. So we'll multiply their entries and coordinate wise, and then we'll take the sum. So in other words, standard matrix multiplication involves performing sum of products. So you multiply the entries product, that is, you take their product and then you sum all those products. So in other words, standard matrix multiplication means that you are performing sum of products. Now suppose I define a new matrix multiplication, which is based on not performing sum of products, but maximum of minimum. So in other words, here we are doing sum of products. In this new matrix multiplication, we'll do maximum of minimum. Or more broadly, we'll take supremum of I. So sum is replaced by supremum and product is replaced by minimum, or more generally, any T norm I. Then, with respect to this new matrix multiplication, what exactly is the matrix multiplication of R and Q? It's precisely this thing. Sum is replaced by supremum product is replaced by minimum, or basically or broadly a denom I. But this is precisely the matrix representation of composition of R and Q. So in other words, if I were to compute the composition of R and Q, that is, we want to compute the membership matrix of R and Q, I'll simply write R and then I'll write Q alongside it, and then we'll perform, instead of the standard matrix multiplication, this new matrix multiplication star I, which involves taking maximum of I or supremum of I instead of sum of products, that is which is done in the standard matrix multiplication. Okay, so I hope you got what I wanted to establish. So I will take an example to make that idea concrete. So this was the relation that we were dealing with, right? So this was the membership matrix of R, and this is the membership matrix of Q. Now we want to compute the membership matrix of composition of R and Q with respect to minimum T naught. So we are interested in this. So how we will do that is like this. So you simply write the membership matrix of R, and then you write the membership matrix of Q. So this is a 2 by 2 matrix. This is a 2 by 3 matrix. And instead of taking the standard matrix multiplication, you take this new matrix multiplication. And this involves taking maximum of min instead of sum of products. So the resulting matrix would be a 2 by 3 matrix. Now let us compute the 1, 1 entry of this matrix. So that would mean, so if we were performing the standard matrix multiplication, we would take this column with this row, and we would multiply it with the first column of Q. But here we are doing maximum of minimum instead of sum of products. So we'll first take the minimum of 0.4 and 0.7. So that is 0.4. We then take the minimum of 1 and 0.8. So that is 0.8. And instead of adding them, we then take the maximum. Similarly, let us compute the 1, second element of this matrix. So that would involve, maybe I should, okay, there's enough space. So we'll look at the first row of R and the second column of Q. Ideally, in the normal matrix multiplication, we would be multiplying we will do the products first and then add them. But here we are taking minimum first and then taking the maximum. So minimum of 0.4 and 0.4 is 0.4. Minimum of 1 and 0.5 is 0.5. And then we'll simply take the maximum. Similarly, to compute 1, third element of R composition Q, we'll look at, again, the first row of R and the third column of Q. And instead of doing sum of products, we'll take maximum of minimum. So minimum of 0.4 and 0.8 is 0.4, and minimum of 1 and 0.9 is 0.9. Similarly, now I won't emphasize the entire process over and over again. So to compute second 2, 1 entry of this composition, we'll look at the second row and first column. So minimum of 0.9 and 0.7 is 0.7, and minimum of 0.2 and 0.8 is 0.2, and we'll have to take their maximum. Similarly, to compute the 2, 2th entry of this matrix, we'll look at the second row and second column. So minimum of 0.9 and 0.4 is 0.4. Minimum of 0.2 and 0.5 is 0.2. Similarly, to compute the 2, third entry of this matrix, we'll look at the second row of R, third column of Q, and we'll do maximum of minimum. So minimum of 0.9, 0.8 is 8. Minimum of 0.2 and 0.9 is 4. So in other words, this essentially becomes 0.8, 0.5, 0.9, 0.7. So using this matrix multiplication idea, we can easily compute the composition instead of individually computing each membership tediously. We can look at them as some kind of matrix multiplication, and that makes things really sort of efficient. So, did you all understand how we can obtain composition of R and Q as some kind of matrix multiplication of membership matrix of R and membership matrix of Q? Is there any doubt? Is the idea clear? Okay. So Jaya says yes. So we'll move on. Okay. So let us now do a question. We have three universes, X, Y, and Z, and we have two relations, R and Q. R from X cross Y, from X to Y, and Q from Y to J. Okay. So the first thing that you should do when you are given a fuzzy relation is look at the matrix and just label them like this so that there is no confusion. Rows corresponds to entries of X. That is the basically the first set. So if R is a fuzzy relation from X cross Y, and you look at the membership matrix of R, then the rows would come from the first universe X, and the columns would correspond to elements to the second universe, which in this case happens to be Y. So, anyways, we have to identify which of these four options are correct. Okay. So, first one has to do with the cardinality of composition of R and Q with respect to minimum T norm, or basically the maximum composition. So, we'll quickly compute that. So instead of doing the usual matrix multiplication, we will do max of mins. So the resulting matrix would be a 2 by 2 matrix. And what would be the 1 comma 1th entry of this matrix? We look at the first row of R and first column of Q. And instead of doing sum of products, we'll do max of mins. So what is minimum of 0.9 and 0.2? It is 0.2. What is minimum of 0.2 and 0.1? It is 0.1. And what is minimum of 0.3 and 0.1? Again, it's 0.1. And we'll do the maximum of these three numbers. Similarly, to compute the 1 comma 2th element of this composition matrix, we will look at the first row of R and second column of Q. And then we'll do max of mins. So minimum of 0.9 and 0.7 is 0.7. Minimum of 0.2 and 0.5 is 0.2. Minimum of 0.3 and 0.3 is again 0.3. Now we'll compute the 2 comma 1th element of this composition matrix. So we'll look at the second row of R and first column of Q. And we'll do max of mins. The minimum of 0.1 and 0.2 is 0.1. Minimum of 0.3 and 0.1 is again 0.1. And minimum of 0.7 and 0.1 is again 0.1. And we'll do the maximum of these. Now to compute the 2 comma 2th element of this composition matrix, we'll look at the second row of R and second column of Q. And instead of doing sum of products, we'll do max. So minimum of 0.1 and 0.7 is 0.1. Minimum of 0.3 and 0.5 is again 0.3. Minimum of 0.7 and 0.3 is 0.3. So this becomes 0.2, 0.7, 0.1, and 0.3. So this is basically how our membership matrix of composition of R and Q looks like. And now we have to compute the cardinality. So we'll simply add, so the cardinality of is the sum of all the values that the membership function of this relation takes and that membership function is compactly represented using this matrix. The entries of these matrix. So this is point 2 plus 0.7 is 0.9, 0.9 plus 1 is 0.9 plus 0.1 is 1 and 1 plus 0.3 is 0.3. So the cardinality of the composition of R in Q is 1.3. So the first option is correct. Okay. And what is the of the composition? So remember height of a so given a fuzzy set AX, the height of A is nothing but the supreme of its membership function. So in other words, membership value. What is the maximum membership value that this fuzzy relation R composed Q can attain? It's 0.7. This also is correct. And what is the domain of? Now, the option C and option D are about composition of R and Q with respect to bounded T norm. So I hope you recall M is minimum T norm. The subscript is used to denote minimum T norm. And B is used to denote bounded sum T norm. So just to recall, this is how the bounded sum T norm looks like. Okay. Now let us compute the composition of R and Q with respect to the bounded sum T norm. The membership matrix of the composition of R and Q So instead of doing maximum of min, we'll do maximum of IB. Okay, and this is how IB looks like. So this is a 2 by 2 matrix. This is a 2 by 3 matrix. This is a 3 by 2 matrix. So what we get is a 2 by 2 matrix. What would be the first 1 comma 1th entry of this matrix? You'll have to look at the first row of R and first column of Q. And instead of doing sum of products, we'll do some maximum of IB. So 0.9, 0.2, 0.2, 0.1, 0.3, 0.1. Similarly, I'll compute 1 comma second entry. That again is obtained by looking at the first row of R and the second column of Q. So this is how the membership matrix of R composition Q with respect to bounded sum T norm looks like. Now, what is this value? Bounded sum T norm applied to 0.9 and 0.2. It's essentially 0.1, right? So 0.9 plus 0.2 is 1.1. 1.1 minus 1 is 0.1. And maximum of 0, 0.1 is again 0.1, right? So I'll quickly do these computations. You can do them yourself and see that these are the values that you get. So this is 0, this is 0, and this is 1.6. So this is 0.6. and this is 0.4, this is 0, this is 0, this is 0, this is 0, points in yes, this is 0, this is 0, this is 0. So maximum of 0.1, 0, 0, maximum of 0, 0, 0. This is nothing but 0.1, 0, 0, 0.6. So this is how the composition of R and Q with respect to bounded sum T norm looks like. The third option is about domain of this composition. So R composition of Q is a fuzzy subset over X cross Z. That is, it is a fuzzy relation from X to Z. So the domain of this relation is going to be a fuzzy set over X, and the range of this relation is going to be a fuzzy subset over Z. And how is the domain obtained? Simply by taking the maximum membership in each column. So this is a membership matrix of R composed Q. So the maximum membership in the first row is 0.6 and the maximum membership in the second row is 0. This is 0.6 and 0. Similarly, the range of R composed Q, which is a fuzzy subset over Z. How do I obtain these membership values of this fuzzy set? You look at the membership matrix of R composed Q, and then you look at the maximum membership in each column. So 0.1 and 0.6. So this again is correct, and this is also correct. So in this case as well, all the four options are correct. So was the question clear? Was the solution clear? Can someone confirm if okay? So moving on. So we have talked about binary fuzzy relation from some universe X to some universe Y, right? And then we defined their domain, range, and then their composition. And we did a couple of questions on them. Now, binary relations can be categorized into two types: homogeneous binary relations and heterogeneous binary relations. So if both the universe X and Y are same, they are called as homogeneous binary relation. And if they are different, then they are called as heterogeneous, right? So when R is a homogeneous binary relation, we simply say that R is a binary relation on X, right? Because there's no need to specify Y, as Y is equal to X. Now, let us for a while look at homogeneous crisp binary relations. So homogeneous crisp binary relation R on X is simply a crisp relation on X. That is, it is a crisp subset of X cross X, or in other words, a member of the power set of X cross X. X cross X. Now, if our underlying set X is finite, suppose X is A, B, C, and I define a relation R like this: A, C, B, C, and C, B. So we have a set X consisting of three elements, and I defined a relation R from X to X that is a homogeneous relation on X like this. Then we can denote this relation using a 0, 1 valued characteristic matrix. We just saw that fuzzy relations are represented using membership matrix, and classical crisp relations are represented by characteristic matrix in case the underlying universe is finite. So in this case, this relation R can be denoted like this. So notice, since X is equals to Y, your columns as well as your rows would correspond to elements of X only. So since A is related to A, we'll have one here. Now A is not related to B, so you cannot find that B here. which means A is not related to B. Therefore, this is 0. A is related to C, so this is 1. Is B related to A? No. Is B related to B? No. Is B related to C? Yes, so 1. Is C related to A? No. Is C related to B? Yes. Is C related to C? No. So a crisp relation on a finite set X can be represented using a membership matrix, which is nothing but a matrix, a binary matrix having value 0 and 1. Now, an alternative way to look at a binary relation on a finite set, a crisp binary relation on a finite X, is using a directed graph. So in this case, X had 3 elements, A, B, and C. So suppose I have 3 nodes. So we have a A here, we have a B here, and we have a C here. Okay. Now A is related to itself. So what we will do is that we will make this loop indicating that A is related to A. Now A is not related to B, so we won't draw anything between A and B, but A is related to C. So this is an undirect. Okay, so this is very direct. A is related to C. Okay. Now is B related to A? No. B is also not related to B, so we won't draw anything between B and B and B and A. But B is related to C. So therefore we'll draw a directed edge from B to C. Is C related to A? No. So we won't draw anything between C and A. Is C related to B? Yes. So we will draw a directed edge. So something like this. Is C related to C? No. So we won't draw anything. Right? So in other words, this crisp relation R on a finite set X can be identified by this directed graph. And it is useful to look at relations that way, because then you can use ideas from graph theory to better understand binary relations. Anyways, now let us consider homogeneous fuzzy binary relations. So a homogeneous fuzzy binary relation R on X is simply a fuzzy relation on X. That is, it is a fuzzy subset of X cross S, or in other words, it's a member of the fuzzy power set of X cross X. So now we have already seen that such a relation on a finite set X can be represented by a membership matrix. So suppose X is A, B, and C, then we can have a relation like this. Right? So this membership matrix essentially lists out the different values that the membership function of R takes. Now we can also denote this graph using a this particular relation R using a directed graph R. Instead, in this case, in addition to that, we'll have weights on each edge. So when we are dealing with crisp relation, it is either the case that 2 elements are related, or it is either the case that they're not related. So that situation can